has n vertices and m edges. And you can also say that the graph has f faces, because once the planar graph is given to you, no matter what plane drawing of the graph you select, the number of faces will always remain the same. We want to say that the number of vertices minus the number of edges plus the number of faces is equal to 2. It's exactly what we wrote the other day. Just the number of faces can be obtained this way. It's just regrouping the terms. Okay. So at the end of the lecture last time, someone had asked this question, right? Why should we look at these drawings and consider proofs? Why don't we try a proof that does not probably depend this much on the drawings? So let's try a proof like that, and then we'll get back to our constructive proof if necessary. So this time we are going to do a proof. So given a graph G that is linear, we are going to do an induction on the number of edges. So if the number of edges is just 1, then it means that there is an edge E like this, which means that the number of vertices is 2, the number of edges is 1, and there is just one face, right? The exterior face is 1. And this also satisfies that n minus m plus f is 2. So now let's assume that in any planar graph, simple connected with less than k edges, we have that n minus m plus f is 2. So this is the inductive hypothesis. Now let's try to do the inductive step. So what does this mean? If you consider any planar graph, let's call this graph GK. The number of vertices mk minus the number of edges mk plus the number of faces fk is equal to 2. So now we have to go to the induction step. So in the induction step, you have a graph G where there are k plus 1 edges.
If you don't mind, can you use V for vertices, E for edges? Then it's easier to follow.
Okay, let's do that. If that's fine with everybody. I don't know.
Yes, ma'am. That.
Sure. Okay. So you want V minus E plus F. Is that what you're saying?
Yes, ma'am. Yes, ma'am.
Sure,
Thank
sure,
you,
sure.
ma'am.
Okay, so V vertices, E edges. Okay. Let me just change everything. That's fine. Okay. Let's change this one. So there are BK vertices minus EK edges plus FK faces. That's equal to 2. So this is what the inductive hypothesis tells you. Now you want to look at a graph where there are k plus 1 edges. So you want to use the inductive hypothesis, and you are given a graph G. Let's call this graph G, and it has k plus 1 edges. Now I want to get to a graph with k edges. So to do that, I need to remove an edge. But only then I can use the inductive hypothesis. Now, how will the graph look like if you remove an edge? That's what we want to see. So it could be something like this, right? So here is the edge. Let's call this. I wanted to call it E, but let's call this something else. Let's call the edge maybe E tilde, if that's fine. Right? So you have an edge E tilde. So what we are saying is, you look at the graph G and consider the graph G minus this edge E tilde. So this has 2 vertices which are incident on E tilde. Now it can have some other parts here. This is the graph on k plus 1 vertices, k plus 1 edges. Now what we are going to do is, we are going to remove this edge and you will get another graph, right, which is on fewer edges. So this graph G minus E tilde is on fewer edges, fewer than k plus 1 edges. And how many connected components can be there in this graph? So one thing you must remember, it's not necessary that this is the structure, right? So in this case, what we are looking at is, so let's write this down. In case 1, this E tilde is a bridge in G. Right? That's the first case. Is everybody clear with this? Like what is going on? Otherwise, we can just redo the whole thing. So you have you are given a graph with k plus 1 edges. You want to use the inductive hypothesis, so you're going to remove one edge, and you don't know what the structure of this edge will be. As a first case, let us consider that this edge is a bridge. So if it's a bridge, what does it mean? Once you remove the edge, the graph will be disconnected. Right? So you know that this graph G minus E here, right? It's on fewer than k plus 1 vertices and is disconnected. Now the question is, how many connected components can it have? So this is in the first case. Right? So let me write it. Now how many connected components can this graph have? G minus suppose it had, let's say, three connected components, right? So what do we mean? After I remove this edge, I get three connected components. That means that originally itself, the graph had two connected components, correct? But we assume that the given graph is a connected graph. So this has exactly two connected components. Is this clear?
Yes, ma'am.
So let's call these two components C1, C2. So this is my C1 and this is my C2. So what do I know about C1 and C2? They are both on fewer number of edges. So I can use inductive hypothesis. Okay, so let's say C1 has V1 vertices, V1 edges, and F1 faces. Similarly, C2 also has V2 vertices, V2 edges, and F2 faces. So this graph, what are the things we know about this graph? So this graph is, so it has two connected components. And both these components are also simple, they are planar, and each of them are connected. So you can apply the inductive hypothesis because these are fewer than k, like less than or equal to k edges. Now let's so what is the relation we know? We know that V1 minus E1 plus F1 is 2 and V2 minus E2 plus F2 is 2. This is from the inductive hypothesis. Now I want to use this to get a relationship between the number of vertices, the number of edges in the faces in this graph. So how many vertices V are there in this graph G? So this is the graph G. So there are V1 plus V2 vertices. You did not remove any vertex. What about the number of edges? It's E1 plus E2 plus this one, right? So this is for the edge E tilde. So this is in G, these relations. Now what can you say about the number of faces? That is, how do you connect F with F1 and F2?
It should be F1 plus F2 minus 1 because the external region will be counted.
So if you look at the regions in this C1, right? Let's say it has F1 many faces. And C2 has F2 many faces. But one thing you must remember is the external face, right? For both C1, which is this portion, and the external face for C2, the exterior region, are common. So it would have, the exterior region would be counted once in F1 and once in F2. So you have to subtract that. So this is for the exterior region. The overcounting that happened in F1 plus F2. Is this clear to everybody? This relation? Okay, so then let's look at B minus E plus F. This is B1 plus B2. So then you will get this. This is 4 minus 2. This is in the case when this edge that we remove is a bridge. Now it could be that the edge that we remove is not a bridge. Okay, so that's the next case we have to consider. So case 2 is not a bridge. So what does it mean? It means that even if you remove E tilde from the graph still remains connected. There's only one connected component. So G minus. So let's look at this edge E tilde. Now, any edge in a planar graph, you know that is either counted twice in the same region or it is in the boundary of two regions. So it will be counted once in this region and once in the other region. So it is counted twice in the same region. So what do we mean by that? It's interior to some region. For example, it will be like this. Let's call this E tilde. And then there might be a graph like this. Or it might also be like the one we saw yesterday. For example, this one. Right? Then this edge E tilde, this one is counted twice in this region when you count the degree, if you remember. Right? So either it can happen like this, or it could be something like this, where it is in the boundary of two regions. So this is R1, this is R2. So these are the only two possibilities. Are people convinced about this? So it's like this edge either is interior to one region, or it belongs exactly to only one region, or it is in the boundary of two regions. These are the only two possibilities. In fact, even this you can think about it as a bridge because this vertex will be removed from the graph, but let's not do that. So what is the number of vertices? Now what I'm going to do is I'm going to remove this edge and I want to apply inductive hypothesis to this, which I know is valid, right? So if you look at this graph, when I mean this graph, only this portion, I know that the number of vertices minus the number of edges plus the number of faces is 2. Right? Now I want to look at the entire graph. So for the entire graph, B is BK plus 1, right? 1 for this vertex. And the edge EK is EK plus 1. Now what can you say about, so let's not EK, just write B. What can you say about the number of faces in terms of the number of faces of this portion here and the graph that you obtain after removing the edges?
Same.
Should remain the same, right? So it will be FK. So you will still get the relation that B minus C plus F is equal to 2 by inductive hypothesis. So now we want to look at just a minute. This is what this is. Okay. So now let's just look at this set. Now here if I remove this edge E, the number of vertices will not change. So the number of vertices B is exactly the vertex that you obtain in the graph CK, which is after removing the edge E. Number of edges certainly is 2 plus 1. This 1 is for the edge E. What can you say about the number of faces in this entire graph in terms of the number of faces of the graph that you get after obtaining, after removing E tilde? So just to make the notes clear, I want to say that PK, EK, FK are in G minus E. So it's the number of vertices, number of edges, and number of faces in the graph G minus E tilde, which is on less than or equal to K edges. So what can you say about the number of faces? Now after I remove this edge, initially what were two regions will now be merged into one region. Right? So the number of regions has gone down by 1. Right? In other words, what can you say about the number of faces in this graph?
K plus 1.
A plus 1. Is this clear to everybody? So then again from this also you will get so this is the proof that does not involve the constructive argument. I think this is sort of cleaner than what was presented the other day in class. But anyway, I'll give a pointer to the constructive argument. So there is also a constructive proof that we did last time. So that can be found in section. So if you want to take a look at it, you can take. It's exactly similar to what we did, but it's more constructive. It's not inductive. I think that the proof that we presented today is much better than discussed today is much better than what was done last time. Okay, so is this clear?
Yes, ma'am.
Okay, so one application of this we had seen last time, right? You can relate the number of edges and the number of vertices, and that way you can also show that K5 is non-planar. So this is like a really powerful formula in planarity. I want to find show some other application which will be used later on in the lecture. So here is a nice observation. Simple. Let's also assume connected. There is a vertex of degree. So let's try to prove this. Okay, for the sake of contradiction, let's assume that every vertex has degree at least 6. So let every vertex. Then what can you say about the sum of the degrees of the vertices? You know that this has to be at least 6n. But what is this? This is exactly 2m, right? Which is the number of edges. So we have that m is at least 3n. So what do you get from this? Can the number of edges be this large? Can it be at least 3n in any planar graph?
No.
So this is strictly greater than 3n minus 6, which is a contradiction. Because we proved that in any planar graph, the number of edges must be at most 3n minus 6. Which means that if you consider any simple planar graph, you will always find a vertex that has degree at most 5. So here is an interesting application of this. Stripes. Consider any planar graph. What can you say about the chromatic number of any planar graph? Is there any guess? The coloring. So what I want you to say is you are given a planar graph. They want you to color the vertices such that no two adjacent vertices get the same color. And how many colors are needed? The hint is use this. So let's say you're given a planar graph. So now I know that there is a vertex. So if the planar graph has, let's say, only 4 vertices, then anyway you can color it with 4 colors. But let's say you are given a planar graph that has lots of vertices. But you always know that irrespective of the number of vertices in a planar graph, there is always one vertex that has degree at most 5. Right? Which means that there is a vertex PNP, degree of P is 5. Let's look at this vertex. So it has 5 neighbors because its degree is 5. And it might be the case that you may have to give different colors to all of them. Right? They may all be adjacent. Whether this is possible, we need to see, but I'm just going to give some colors. So now, if I remove this vertex from the graph, what can you say about the resulting graph? So now I want to color V. I've given all its neighbors like different colors, and I have to give a color to V. Let me give V also a different color, let's say black. So far I've used 6 colors, right? Now the question is, if I remove this vertex V, will the graph be still planar?
Yes.
So G minus V square. So if you use an inductive argument, you can assume that this can also be colored with 6 colors. So just the fact that there exists a vertex of degree 5, right, tells you that planar graphs are 6 color, which is not true about general graphs. Right? For general graphs, you would want to say that you have to bound the maximum degree in order to bound the chromatic number. But here, with just the fact that there is one vertex of degree at most 5, you're able to say that the planar graph is 6 color. Right? So the chromatic number is at most 6. Now the question is, can you get a better chromatic number?
Can you explain this thing again? How is it 6 colorable?
Okay. So let's consider a planar graph. You know that there is one vertex that is degree at most 5, right? So let's say that B is that vertex. You look at that vertex. Maybe I should have done it, just given the answer and then the argument. So there is one vertex, you know, it has degree 5. So let's put 5 neighbors. And you use at most 5 colors for them, right? If there are 5 neighbors, in the worst case, all of them will get different colors. And use, now consider the graph that you remove the vertex B and consider G minus. So this is by induction. So let's assume that for all graphs, so it's an induction on, maybe I will just do this. So it's an induction on the number of vertices. So let's assume for the graph has n vertices. For fewer than n vertices or n minus 1 vertices, the graph is 6 color. The planar graph is 6 color. So now I know that G minus V is 6 color from the inductive hypothesis. So what do I have to do? I have to put back V inside and ensure that this graph is still 6 colorable. The rest of the graph I have obtained the coloring from the induction. So it's the rest of the graph. Once I color, I will get colors for all vertices except V. Now I have to only color the vertex V. In the worst case, all the neighbors of V might get distinct colors. So give V a color that is different from all of them. So you will need one extra color for. So in all, you can color the graph in 6 colors. This is because if you remove a vertex from a planar graph, it still remains planar, and you know that there is a vertex that is degree at most 5.
Got it, ma'am. Thank you.
Is this clear to everybody? Like we can do this again. Okay. So now,
Why does this fail for normal graphs?
okay, so for normal graphs, the first thing is there can be a K6, and you will have to use like 6 colors or 7 colors. There can be a K7, right? This sort of intuitively stems from the fact that there is no K5 sitting inside. The main thing is, if you wanted to say this for normal graphs, then you should have said that the maximum degree itself is 5. That's why I'm able to bound the chromatic number by 6. But whereas here you have just like one vertex degree. So the main thing is that non-planar graphs can be very dense. Like there can be lots of edges. Whereas in planar graphs, the number of edges is at most 3 and 6. You cannot have that many edges compared to the number of edges. This is, yeah. So even now we don't have like good lower bounds on the chromatic number of graphs. Only for special graph classes we know this. That's like a research question. Like we are given a graph, you know some more information about it, some structure. Can you bound its chromatic number? Can you say that it's at least this much or at most this much? So one way to bound it is the click number. So in essence, a normal graph can have a click of size 7, and you might just need 7 colors. You cannot do anything about it. Whereas that will not happen in a planar. Okay. So if that answered the question, then we want to actually. Okay, let me just go ahead. So this is an observation that it is 6 color. So let's look at another. So one question that naturally comes up is, can you improve this? For example, do we actually need 5 colors for the neighbors? So intuitively, suppose you just needed to use 5 colors for the neighbors. Like there was no other way. What can you say about these 5 vertices? You're given a planar graph and you are in a fix in such a situation that there are 5 vertices for which you need to give 5 distinct colors.
It's a complete graph.
So then this means that there must be an edge between every pair of vertices here, right? So there's a K5 sitting inside. But can that happen?
No.
It cannot happen, right? Because K5 we saw is non-planar. So if it sits inside some graph, for whatever sits inside means, I have to define that. If it sits inside some graph, then that graph should also be non-planar. If you are able to somehow nicely draw that graph on the plane without drawings, you can just remove all the other edges and you would have got a plain drawing of K5 also, which we saw is not possible. So that is something we have to use now. So maybe you can do better than just 6 colors. That's the next observation. That planar graphs 5 colors. Let's do a proof of this. This is an induction and the number of vertices. So we know that in any planar graph there is a vertex degree at most 5. So now when we say degree at most 5, let's call this vertex V. The degree of V could be less than or equal to 4 also. So if this is the case, what you could do is just consider the graph G minus V, like what we did last time. Use the inductive hypothesis. So what is the inductive hypothesis? That any planar graph less than n vertices. Right. So G minus V is on less than n vertices. This is 5 colorable. Now you look at G minus V. You say this is your G minus V, and you have to put back V. Right? And you know the degree of V is 4. So it's connected to at most 4 neighbors here. You give all of them distinct colors. Right? In the worst case, this is like violet. Now you can give some other color to V. Let's say blue. And the graph is still 5 color. So G is 5. So whenever the degree of the vertex V is less than or equal to 4, this is fine. So the only case we need to consider is when degree of V is 5. Is this clear? Like this case?
Yes, ma'am.
So now we are in the case when the degree of V is exactly 5. So you know that the graph is planar, so G has a vertex of degree 5. That vertex is V. And let's say there are 5 vertices. V1, V2, V3, V5. Now let's use the observation that we just saw. Right? That V1, V2, V4, V5, they cannot form a clique. Okay? So this means that there is definitely at least one pair of vertices that are not adjacent to each other. Let's take their V1, V3. So, this edge is not in G. So now what do we do? We know that this edge is not in the graph. So ideally what you would think is I can give these two the same color, right? Because anyway that won't affect them. But now we also need to argue that if we give these two red, then everything else is satisfied. Like V1 might have other edges, right? V3 might have other edges. You don't know. For example, if you try an inductive argument, what would you do? You would remove V and say that the exact same argument, right? G minus V, this portion is 5 colorable. But then in that 5 coloring, this might get red, this might get blue, right? And there might be another neighbor that is attached to this that has red color. Now suddenly I cannot change both of them to red. Right? Then I'll get a conflict. So I won't get a proper coloring of the graph G by using induction. Is this clear? Like whatever I just said, or was it too fast?
Yeah, it's clear. Yeah.
So this directly saying that just color these two with same color is not the right way to do it. Right? That should be clear. Right? So we have to do something clever. So now this is what we will do, and here is what this will get us to a new concept, which is called. So let's consider this case. Okay, so there is some graph here. I don't know what it is, but let's draw it this way, and let's say there is a triangle here. Of course, there could be other things here. There could be a K4 here. Right? So what I'm trying to say is that each of these vertices are connected to other edges. I mean, other vertices by edges, which we don't know what they are. And the only thing we know is this vertex has 5 neighbors. This vertex B has 5 neighbors. That's its only information we have. So now, if I contract this edge, so what do I mean by that? I sort of compress this line into just one pole here. In other words, so what do we mean by contract? So what we are trying to say is you have an edge E and it has 2 endpoints x, y. You remove the edge E from the graph. And merge x and y into one vertex. Right? So you'll just get one vertex, x equal to y. Now suppose there was a triangle here, and let's say there is a K4 here. Everything will now become part of this vertex. So what will happen after you contract E? You'll get one vertex, which is x is equal to y, and you will have a K4 attached to it.
So basically, all the neighbors of V1 will get transferred
Exactly.
to V. I mean,
Right.
to be the neighbors of V.
Neighbors of so
All,
what do you say? All the
all the
neighbors of
neighbors
V1.
will be transferred to V, right?
Exactly. And then everything else remains as is. Right? So you can see that you identify. So this is also sometimes called as identify x with y, meaning that both these vertices merge into one big vertex. So you can just merge these two and draw a circle, and then everything that was adjacent to V1 will now be adjacent to V. So that's what we mean by edge contraction. So this is a very important operation that is done on graphs, and even when you go ahead with your masters, you will see that in other courses you do these operations to get a smaller graph, right? Graph from fewer edges that has more structure, and then you work with that small graph and then put back, like stretch back the edges to see what happens. So in our case, is this edge contraction thing clear?
Yes, ma'am.
Okay. So now what we are going to do is, we know that V1 and V3 are the chosen vertices that are not adjacent. So let's contract these two into V. So you have a big blob in V, and all the neighbors of V1 become neighbors of V, and all neighbors of V3 also become neighbors of V. This is very important. So now what are we going to do? We are going to contract the edge dV1 and dV3. And just copy paste this picture here. So now, so after contraction, how does the picture look like? Right? So it will have V, there will still be V2, V4, V5. Those three things will remain untouched. And then there are these other portions. There is a triangle here. And so now the most important thing to remember is after edge contraction, the graph is on fewer number of vertices. At least one vertex would have gone out, right? V1 and V3, both we have contracted into V. So it's on fewer number of vertices. After edge contraction, this one, fewer vertices. and it is still planar. So that's very important in the sense that edge contraction does not affect the planarity. It's just merging vertices. So the graph is still planar. So now you can still use the inductive hypothesis. And you know that this graph, right, G after contraction can be phi color. So now what does it mean? There is a phi coloring, right, in which this vertex will get some color. Let's say it gets pink color. Right? And all its neighbors, which were V2, V4, and V5, will all get distinct colors. The other things will also get distinct colors. Now I know that I have a phi coloring which assigns colors to all the vertices. Right? So it will assign colors to V2, V4, V5, and so on. And also this new V. Right? The new V, or this new V. Right? So now to get the proper coloring of the original graph from this coloring, I must color, or I must find colors for V, V1, and V3, because V1 and V3 are merged to get V. So now in the new graph, there won't be any V1 or V3. All of them are just the blob here, right? And I've given this blob pink color. Now what should I do to get a proper coloring for these three vertices?
Expand and then uh, give the fifth color to the center.
And what colors to V1 and V3?
The same color.
So let's do what he says. So the color of V1 in the graph is the color of new V. Color of V2, V3 is also the color of V. And color of V in the original graph is the fifth color. Let's say violet. So assuming I have used 4 colors and violet has not yet been used. Is this a proper coloring? So let's just check that. So for this to be a proper coloring, there must be no neighbor of V1 that gets the color of new V. So that is pink color. Right? It will not. Right? Suppose it did. Suppose there was an adjacent vertex such that 2 of them were colored pink. Then these 2 would have been colored pink in this graph. So then there means that the induction was incorrect. Right? In the inductive hypothesis, you assume that you got the right color, a proper color. So there are no 2 vertices that get the same color. There is nothing adjacent to V1 gets the color of V1. And since you used only 4 colors right now, right, you are left with 1 color for V. Is this clear to everybody with the entire argument? In essence, in the original graph, what you'll get is the following. So let's say that V will, in the end, V will get purple color, and V2, V3 get pink color, let's say, and V4 gets green, V5 gets red, V2 gets yellow. So you have used 5 colors. The color of every other vertex will be taken care of by induction. So this proof I just demonstrated so that you understand what edge contraction is. You may have to see that later on also. But there is an alternate proof. I just want to give reference. So this is a proof where what is called a Kempe chain argument. Is not required for the course, but if you're interested and want to like do some coloring experiments, you can try this. Okay, so this does not use any edge contraction, but if you look at just V1, V3 and try to recolor, right? If you look at what edges go out of V1, how to recolor them, what edges go out of V3, what colors to give them without doing this edge contraction. So it's also a very nice argument and it's used widely in coloring. So it's good to know that something like that exists, but it's not required for the course. So if you don't get time to like, take a look at it, it's fine. But is this argument clear?
Yes, ma'am.
So now I promised one application in the beginning of planarity. Let's do that. So let's say you have a map. You have the world map with like some 195 countries. And then there are regions like this. Now I want you to color the map such that no two neighboring countries get the same color. So how many colors are required? That's the question. If I wanted you to color the world map with colors such that no two neighbors get the same color. In all probability, if I had asked you this question at the beginning of the course, you would have said like how many other countries there are, or at least as many, like at least half those number of colors. But now can someone say how you model this as a graph? Problem in graph coloring?
Countries as vertices and adjacent countries. Country sharing boundaries has an edge.
Do you want to put an edge if they share a boundary? Right? So these two. So this is the graph that you obtain. Right? The graph G. This way. Is like this clear to everybody? That is, the vertices are countries. And you draw an edge between them if they share a boundary. So what can you say about this graph? What property does this graph have?
Five colorable.
Yeah, so this graph is planar. It's planar graph. It's not hard to see that you cannot find any crossings. And this graph is 5 colorable from what we said. So indeed, it is known that planar graphs are 4 colorable. But we will not see the proof in this course. So this is an important statement in graph theory, that the world map can actually be colored this way in just 4 colors. Very surprising, right? There are like 195 countries and you are using just 2 colors. 194 countries. They're using just 2 colors. I mean 4 colors to color the entire world map. While you would have like expected a few more colors. Did it stop sharing?
Yes, ma'am.
Okay. So this argument we will not see in the course, but it's good to know that this exists. Okay, so yeah. Was there a question?
So the artisan plane, like it's a circle, like it's it's a sphere. So like any manifold which is homeomorphic to that sphere will have this property, right? With respect to this graph, like map color property, 5 color.
What are you trying to show? I didn't get. Are you trying to say that?
Plane graphs we define for just Euclidean plane art, and
Right,
then
right.
we
So if
applied
you
it
try
to
to draw
those
this,
here.
yeah. So you can actually try to draw these graphs on a coffee mug, and you will be able to draw them without edge crossings. I mean, whatever required edge crossings on the plane, if you try to draw them on a coffee mug, on the outside of the coffee mug, you can actually draw it. Yeah. So these things have also been studied. Like, what's the dimension that you have to go to? Right. I think that's what you're asking. So these are called planar embeddings. Like it's that these edges have to cross on a plane, but if you have to draw them on the outside of a coffee mug, you can do it. But these things we will not see in this slide yet. Maybe the course on graph theory might. Okay, so right. So there is something else that I wanted to say about planar graphs quickly. I'll finish in 5 minutes. Okay, so we know that K5 and K33 are non-planar. Okay, so I wanted to show something. Wait, let me see if I can do this. Just give me 1 minute. Let me just stop sharing for a minute. and I will share again. So let's consider the following graph that I draw right now. I should draw it probably better. And then there are 5 more vertices. Now the question is, do you think that this graph is planar? Whatever I just right? Is this graph planar? That's the question. So this is a very famous graph. It's called the Peterson's graph. Is this graph planar? Do you think it is or it is not?
Ma'am, if it were planar, then we could draw it in a plane and I mean, like without edge crossings, and we could contract those like the one which connects the star to the outside pentagon.
Right, and you will get that K5 is planar.
Yes, ma'am. Yes, ma'am.
Right, exactly. So let's see an animation of whatever that was. Okay. Let me just reload that. There's another way to look at it. Is the animation running by any chance? It is, right? So this is the drawing that I drew, the graph. Now you're just sort of combining some vertices and edges and doing some operation. Right? You see some vertices edges are combined, and then you get a copy of K33. If I had just told you that K33, there is a copy of K33 in this graph, I'm sure you would have said no, right? But K5 is something you can see. Like what he said, you can contract the edges so that the inside becomes the outside and you get a K5 sitting inside. In fact, a K33 also sits inside. So what is that operation that is going on in this animation? Right? So initially there was 6, 7, and then those edges suddenly got deleted. What is happening? Right? That's what we want to understand. So to understand this, we have to define, just like edge contraction, we have to talk about another operation, which is called subdivision. So what is a subdivision in a graph? For example, if you have an edge, let's say UV, a subdivision of this edge is obtained by removing UV and adding a vertex, let's say W, and you add two edges, UW and BW. Right? In other words, you just add, you subdivide this edge. Since you add an additional vertex and you add two edges in the place of one edge. Right? Such an operation is called a subdivision, or sometimes called an elementary subdivision. Now, for example, let's consider these two graphs. Yeah, I'm just drawing some arbitrary graph. It should not be planned. Let's consider this. And this graph. So these two graphs, if you see, let's call this G1 and let's call this G2. So G2 can be obtained from G1 by a sequence of elementary subdivisions. Is that clear? G2 is obtained from G1 by a sequence of subdivisions. So first you look at this edge, you add a vertex here, then you add this vertex, and this vertex, and you'll get G2 from G1. So these two graphs, G1 and G2, are
G2 missing an edge. Or
oh, sorry. Yeah, so all the original edges will be retained, but some edges will be subdivided. That's right. Yeah, this edge I missed. So these are homeomorphic. So one way to see what he said was that, right, that you can contract these edges and you will get a k5, which is a nice argument, right? If the original graph was planar, if this graph was planar, then after contracting the edges, what you get will also be planar, because edge contraction preserves planarity. In which case, you will have a drawing of k5, right, which we know cannot happen. So that's a nice way to argue. But another way to see this is via subdivisions, right? So what you did was just introduced some additional edges. So if the original graph is non-planar, then even after you subdivide, that nothing much can change. So it's not. So one thing we saw is that k5 and k3 are not planar. But if you know that a graph is not planar, like what is it? Definitely k5 or k33 cannot sit inside the graph. As a subgraph, it cannot sit inside. In fact, more is known that it cannot even be, it cannot contain a copy of k5 or k33 this way. Like you cannot subdivide to get a copy of k5 or k3. So let me just write the statement. So this is a theorem due to. It says that a graph is non-planar if and only if it contains no subgraph that is homeomorphic to k5 or k3. Okay, so is the statement clear? It's not just that it should not contain a copy, it should not have k5 or k3 as a subgraph. It cannot even have a subgraph that is homeomorphic to k5 or k3. So this is a very strong statement in the sense that
Should it be planar?
oh, if it contains, oh yeah, this knows probably not there. I will just write this. Okay. So in the sense that if it contains k5 or k33, I know the graph is not planar. And maybe it's okay to say that if a graph is not planar, then some copy of either k5 or k33 should only sit inside the graph. This is like very strong. There is nothing else. So that outside k5 or k33 that is important for planarity. So this is a very strong theorem. It's quite important, but we will not see a proof of it. It's a bit involved. Maybe the course on graph theory will, but it's good to know that these things exist. So such theorems are called forbidden subgraph characterizations. So generally you are given a graph class and it has some structure. You can say that this graph class has this structure if and only if these things don't exist in the graph. Right? So these, so k5 or k33 are forbidden as subgraphs for a graph to be planar, non-planar. These things are called forbidden subgraph characterizations. Yeah, these will probably come in masters. You won't see this elsewhere. But it's good to know that this thing exists. Such theorem. We won't see its proof. Okay. So the underlying point is only k5 and k33 matter for planarity or non-planar. So yeah, this is probably all that I want to say. More it is. Yeah. So is Partha around by any chance?
Yes.
Okay, so would you want to continue with the Ramsey theory or?
Yeah, it's close to 6 now. Maybe I can start probability a little bit. Ramsey will come
Okay,
later.
sure. So I will just stop sharing my screen.
You can keep, probably you can continue recording.
Sure, I'll do it. Yeah. I just stopped sharing. So
So I guess to make, can you all hear me? Is it clear?
Yes, sir.
So I think I think mostly like combinatorics and graph theory is over, and we have around 6, I guess like 6 weeks more. Yeah, I guess 5 to 6 weeks more. So the rest of the course, there could be a bit of miscellaneous topic, and you will use all the things that you have learned in graph theory and combinatorics time to time. Like for example, now I'll start with probability, and there will be some probability theory, a bit of Ramsey theory, and some applications of group theory in combinatorics, maybe a little bit of number theory. This is the plan. And after that, if the time permits, we'll do a miscellaneous kind of topic. That's not yet clear how much time we'll get. But so I guess the course will end by second week of May or something like that, because then you have to take the exams. Okay, so let's start with the probability. So I guess like most of you are also doing or have done another full course on probability, right? That's what you told us.
Yeah, we're doing right now, sir.
You are doing right now another course in probability.
Yes, sir.
So what is going on in probability now?
Discrete random variables.
Okay. And I mean, what is going on in discrete random variable? Can you give me some?
Variance is over, and like last class we were doing some problems related to matchings and
Related to?
matchings and indicator functions.
Sorry, I can't hear you properly. Matchings and
Indicator functions.
indicator. So which book you are following there?
Grimmett.
Okay, so since probability is also is a part of discrete math, I don't know how these things are put in the same semester. I don't know, because that is probably offered from the maths department, right? So what I will do, I will not go into like probability from the scratch, because I expect that you already have enough background. There, of course, there will be some overlap, because this is actually discrete probability. So there has to be some overlap, because when these two courses are independently designed. But I'll try to show you at least something that I guess you have not learned in the math curriculum. Okay, so let's start. So as I said, I will not go into all the technical definitions, because you know it from the other course. So as you all know, this is referred to as sample space. And A is, just to quickly refresh the mind. So this is the event, and the probability of the event is, everything is finite in our situation, so there will be no integration, nothing like that. It's all discrete probability. So in general, if you have to event, I'm giving you a quick recap, so that you don't get bored too much from the overlapping of the math course. Standard, the union thing, and in computer science, mostly like computer science literature, you come across the word called union bound. It's basically means if you take the event A1, A2, AN, like events on the same sample space, then if you take the union of these things, these events. This probability is upper bounded by sum of the probabilities. This basically, I guess you know it. Have you seen this? You must have seen this, right?
Yes, sir.
So this is like inclusion, exclusion for probability and taking only the first term. So this is in CS literature, this is often called union bound. Remember this term, self. Okay, so the main reason we want to study probability here is to apply probability in different concrete problems. So let me straight away begin with a problem uh, which belongs to a subject. It's called probabilistic method. So we haven't spent time on the Ramsey theory so far, but I will not assume anything from Ramsey theory. I will just give you one example from Ramsey theory. So let's look at, I'll define. It is self-contained. Because Ramsey theory is an involved subject. We won't go into that right now. So let me just define the symmetric Ramsey number, which is generally denoted by this notation RKK, R for Ramsey. What is so this is just a definition. So what is the meaning of this number? So it is the smallest. This is just a definition. Smallest positive integer such that if we two color edges of the complete graph so why I'm writing it RKK, that's for the historical reason, because it's coming from the Ramsey theory. We may ignore that at the moment. Then there follows K monochromatic KK complete. Okay, so let's see the definition, what it's saying. So RKK is a special number in combinatorics that is due to Ramsey. It's called symmetric Ramsey number. So what it says is quite amazing. So this is the smallest positive integer such that if we two color the edges of the complete graph, think about like RKK equal to some n. Okay. So take a complete graph on Kn where n equal to RKK. And you color the edge of the graph using two colors, red and blue, in any way you want. Then you can always get a KK sitting inside Kn. It's a complete graph, so there will be KK, which is monochromatic. Either all the edges in KK are red or they are blue. Is the definition is clear?
Yes, sir.
Okay. So this is a basic object in Ramsey theory, and this is not a very simple object to study. There are many, still after so many years of studies, there are still many open problems in Ramsey theory. But today, since our time is very less, so I'll just give you an application, a beautiful application of probability to illustrate a basic result. So let me put this lemma. for k greater than equal to 3. This is just a pathological case because we know it's very well if what happens for R3. If k greater than equal to 3, RKK is 2 power k by 2. So what this lemma says that forget about k greater than equal to 3. That's not very important for us. That value of RKK is always more than 2 power k by 2. Only this much we want to address. Of course, you can always ask what is the upper bound. There are upper bounds, like I think the current known upper bound is that something like 4 power k, but that will require a different method to prove it. At the moment, we just focus on this statement. That means what this statement is intuitively saying, if you start with a complete graph having less than so many vertices, then there is always, you can color in a clever way such that no such monochromatic KK will be obtained. There will be at least one such bad color. Is the definition and what the lemma trying to say is clear?
Yes, sir.
Okay. So these kind of statements are typically called Ramsey style statement, which has fundamental applications in combinatorics, in complexity theory, and pseudo-randomness, and many other branch of computer science. So let's try to attack this thing, how people even prove. Okay, so think about in probability theory. Suppose you want to prove as a general statement. This is not belong to the proof. I'm just writing it generally. Suppose you want to prove some event E happens. Happens means it's not a zero probability event. Sometimes it happens. That means the probability that E is to show that it's enough to prove that it is more than zero. Right? It's a same statement. But in other words, you can also prove. You can also show that the probability of the complement event is not full. That means it is strictly less than 1. If you prove that probability of the complement event is strictly less than 1, that means you know that there is a non-zero probability that events E happens. These are very simple but very golden rule for probability. And this very innocent looking rule is actually played enormous role in even in many deep groups. Okay, so we'll just take this golden rule with us and try to attack this problem. So what are we trying to prove? That means let's consider that value of RKK to be less than 2 power k by, less than equal to 2 power k by. That means you start with a reasonably small graph. I want to prove that there always exists a 2 coloring such that no KK is monochromatic. Okay. Now let's take one kk. I'm not good at drawing that much. So this is not, of course, not k. This is like some k5. So take some kk and let's try to color that kk randomly. Randomly means every edge either I will assign to red color or I will assign to blue color. That's my experiment, right? I randomly select every edge like a blue color or a red color. So my question is that what is the probability that this kk is monochromatic? So this probability is over what? There is a set of colorings, right? What is a set of coloring? Like every set of coloring tau is a map from that that edge set of kn, where n is rkk, to either red or blue, naturally. So this is a color. So from this color, you uniformly sample a color, and I want to estimate what is the probability that kk is monochromatic. Right? So that probability is very easy to understand. What is the probability that this is monochromatic? That's equal to this 2 power k choose 2 is the all possible way to color its edges, because this kk has k choose too many edges, and every edge can be colored like either red or blue, right? And this to make it monochromatic, it could be either red or blue. So this is the probability that one kk is monochromatic. Is it clear?
Yes, sir.
Okay, it's very easy. Now, so how many? So the number of kk in kn is n choose k. Obviously, you can choose any k vertices, and that defines. So let's call this number capital K, and let us say the events u1, e2, en such that ei happens if and only if the ith kk is monochrome. That means this was like probably the first anything. I mean, I just did the calculation for one, so this you could say like this is like u1. So this probability of u1 I estimate. Now let's look at probability of this union of ei. That means this is the probability that one of that kk will be monochromatic, right? And I know that this is bounded by this, but this is, since capital N is this value, this is bounded by n choose k 2 times. So let's divide it. Let's write it 2 power 1 minus k choose, right? Are you okay? Now, by this golden rule of probability that I just wrote, it is enough to prove
Sir, but
yes.
like it's over different random spaces, right? It's over a different sample space.
Sir, can
right?
you explain the last step again?
1 minute, 1 minute. So first, why it is different sample spaces?
Because in the first case, when we
Because it
just
is-
coloring the only the KK, right?
No, I am think about like a global coloring. This coloring is a map from this vertex of this big graph to red and blue. And this probability will be live because the outside things are getting balanced, right? It does not matter. You are only zooming into that one copy of that KK. Not clear. So
Yes,
outside,
it's clear. It's clear. Yeah.
something
Outside
will
things,
happen
yeah,
outside.
yeah.
That doesn't matter for us, right?
Yeah.
So someone asked a second question, yeah.
So yes, sir. The last step. N choose k into 2 to the 1 minus k.
So what is the problem? Capital N is N choose K. You mean this inequality should be exact equality?
No, sir. Can you explain the 2 to the 1 minus k choose 2?
Oh, this 2 by 2 power K choose 2, I just wrote 2 power 1 minus K choose 2.
Okay, right. I get it. Yeah.
So by the golden rule of probability is enough to prove that. So call this event like E. It's enough to prove that P of E is strictly less than 1. Why? That's the golden rule, right? If you prove that P of E is less than 1, then there exists some coloring which has not hit any of the this KK as monochromatic. It's a bit counterintuitive when you see it for the first time. I'm already running out of the time. Think about the complement event. What is a complement event? That none of these are the all possible K complete graph inside that K small n, right? And the that complement event is that none of these complete graphs are monochromatic. That's what I want to prove, that there exists a color. Are you getting the intuition?
Yes, sir.
Yes, sir.
Great. So this is now, once you have this right intuition, it's very easy. So just take this. So this is like n choose k to power. So that's equal to factorial n by n minus k factorial 2 power 1 minus k by 2. So if you divide n factorial by n minus k factorial, what do you get? n minus 1, n minus 2, there are like k terms, right? But all the terms are bounded by n, so this is bounded by n power k. In fact, I should use it's a strict bound. It's less than n power k by k factorial 2 power 1 minus k by 2. Right? Now let n is less than equal to 2 power k by 2. This is the regime where I want to prove that there exists a false coloring, right? Then this will be less than equal to 2 power k square by 2 by factorial k. And now if you expand k choose 2, that is like 2 power 1 minus k into k minus 1 by 2. So how much you will get? So notice that 2 power k square by 2 will get cancelled out, right? So you will get 2, and then you will get 2 power k by 2, and you get factorial k. But this is definitely less than 1, right? Do you see that? Why it is definitely less than 1? It's very clear.
Yes, sir.
Because what is the growth of factorial k? I mean, there are multiple ways to see it. So that if you want, so the basically the growth of factorial k is like it's much more than 2 power k by 2. It is like it's like 2 power
k factorial.
Correct. Sorry. So this is like this log of. So this is like 2 power k log k type growth. So this is the denominator function is rapidly growing compared to the numerator function. This is well below 1. That's it. So this is see this is a sleek argument, right? This completely avoids the graph theory part of the problem. So when I stated the problem, you feel like, oh, I have to do some heavy graph theory to prove it. But the way they proved it, completely different. It just totally different insight to prove it. Notice that I proved that there exists such a false coloring that will not make it monochromatic, any of these k copies. But I don't give you any clue that which coloring is that coloring. Right? I'm not allowing to find that coloring, but in an indirect way, using an existential argument, which is very common in mathematics, I convince you that such a coloring exists. So probability theory is a great tool to prove many combinatorial objects exist. If you don't use probability theory and attack them using graph theory or pure combinatorics, you can have a very tough time. So this is a classic example of probabilistic method, and there is a whole book about it. That book by Alon and Spencer. It's a great book. It's freely available also, but that will require a complete different course on probabilistic method. So we'll just touch very small, tiny things and do it in this course. I guess it's over. The time is over for today. You can stop the recording.
Recording stopped.